fight. All the best, everyone.
Excuse me. Hello, I'm Mladen Matev. I'm a researcher in nuclear physics from Bulgaria, Institute of Nuclear Research. I've been with the IYPT at various levels since 2004 and as an independent juror since 2018. I've been a team leader before on the part of Bulgaria. Wish you good luck and let's see a good fight.
Good afternoon, everyone. I'm Chen Jing from China, and I worked in Nankai University. My major is optics, and I've been in IYPT since 2014. And good luck. Thank you.
Hello, everyone. I'm Becca. I'm from Georgia, but I am as an independent juror. I've been juror for last 4 years on IYPT. Before that, trainer of Team Georgia, and wish you good luck.
Thank you. We will also have 4 non-voting chairs, but I would also like to give, like you to give a short introduction. Can I start just here?
Cool, thank you. So I'm Shun Xingshi from the New Zealand team. Well, I'm a part of the New Zealand team leader, and I actually competed in this tournament in 2019, and I've been coaching the New Zealand team ever since. Me, in terms of my profession, I work as an aerospace engineer.
I'm Mangad. I'm doing a master's here at Lund, and this is my first IYPT, and I'm quite excited to see everyone perform.
And I'm Josephine Sjöholm. I'm from Lund, and I've been teaching physics for 25 years in high school.
Hello, everybody. I'm Zurabi Ogulava from Georgia as well. I've been participating. I've been involved into IYPT since 2019, and yes, almost 5th year in consecutively when I'm participating in some kind of role. Now as a juror, I wish you all the best and fruitful fights.
Thank you very much. Very briefly, I'm Eric. I am a former participant many years ago and currently serve as the treasurer of IYPT. Are there any questions from the participant? I'm still required to inform you that this fight will be recorded. There are 2 cameras here and here. So maybe for my jury colleagues, try not to block the cameras. It's probably more me than Sashikant. But these are the 2 cameras. You will have the microphones. I will pass on the microphone to the reviewer so that we will also have the review on tape. There's a question from the fight assistant. Fantastic. Okay. There are also cameras there, so in case of the audience somebody is uncomfortable being recorded, I think now would be the time to leave. Any questions from the teams? Oh, yeah. Yes. Yeah. The full name, please. I mean, we just need to be able to map you to the person in the CC system. Yes. Right, thank you. All right, if that's all said and done, then we will have the clock over here, and we have 1 minute for the opponent to make his challenge. Problem number 1 was rejected. We have again 1 minute for the opponent, please. Problem 13 was rejected. Okay, you guys are very fast for the timekeeper, so can we have again 1 minute for the opponent for the next? 5 minutes preparation for the reporter, and can I also ask the reporter and the opponent to connect the microphone in time? Thank you.
Test, test.
Hello? Hello? Yay. Do I? Trying. Try not to click any buttons. Okay. If there's a technical difficulty with the microphone mid my presentation, I'll just keep going. If that's okay. I'll just try to speak louder. All right. Hello everyone, my name is Daniel Cui from Team Canada, and today I'll present Problem 7, Ruler Cannon. The problem statement read as follows. Two rulers are tightly held against each other. A round projectile, such as a plastic bottle cap or a ball, is inserted between them close to one of their ends. When an extra force is exerted on the surface of the ruler, the projectile will eject at a high speed. Investigate this effect and the parameters that affect ejection speed. The relevant parameters I've investigated are 1, the magnitude of the applied force, 2nd, the location of the force applied, 3rd, the location of the projectile, 4th, the Young's modulus of the ruler, 5th, the mass of the projectile, and lastly, the radius of the projectile. Here's an overview of my presentation. First, let's go over the phenomenon. We can clearly hear from the phenomenon that as a force applied to the ruler, the disc will be ejected at a high velocity. Here is our overall experimental setup with a light, an air compressor, a board, and tripod for tracking. Here on the board, we can see a clamp that clamps the two rulers with a projectile in between, and with a valve that controls when the air will be applied, will go through the piston that applies an adjustable applied force to the two rulers. Here we have a blocker that's positioned on the other side of the ruler to exert a normal force that's equal in magnitude to the applied force, so the ruler will be squeezed from both ends. And here we have a glass that reduces the friction. Note that we are able to cut slots in the wood to enable the adjustment of the location of the force applied, and also the glass plates will reduce friction. Here we use both tracker and OpenCV to track the velocity of the ball. And to characterize the projectiles, we're able to 3D print both discs and balls that vary in mass and radius. And we're also able to, all dimensions are measured with caliper and analytical balance. And these projectiles can be opened and clay can be put inside to vary the radius parameter while keeping the mass constant. To characterize force, we use the equation F equals P times A. We find the cross-sectional area of a piston multiplied by the pressure applied, and to accuracy to around plus and minus 2 newtons. To characterize the Young's modulus of the ruler, which is the measure of a material's resistance to elastic deformation under tension, we're able to use this equation. And the midpoint stress test was applied for both the plastic and metal rulers to measure the vertical displacement of the ruler when a adjustable hanging mass is hanging in the midpoint of the ruler using a dial indicator. By plotting these two plots, we're able to find the Young's modulus for both the metal ruler to be as 228 gigapascals and that of the plastic ruler to be around 2.99 gigapascals, which aligns with literature values. In order to characterize friction, we use an inclined plane, and we measure the critical angle for static friction as well as the acceleration for kinetic friction. To measure the angle, we use an inclinometer, and here are values for both kinetic and static friction. In order to characterize rotational energy and see if rotational energy is a major part of the experiment, we took several videos, and here we assume the radio, like for example in this video, we assume the ball rotated around half a period over the span of 0.367 seconds. And here we can see that the rotational energy is 4 orders of magnitude lower than that of the translation energy, and therefore we can assume rotational energy to be negligible. Now moving on to our theoretical models. First, I'll give a qualitative explanation. Qualitatively, you can see that when the ball is at rest, the net force in the xy plane is 0. When there's a small applied force, static friction prevents the ball from shooting out. And when the applied force increases, the normal force also increases proportionally, as so does static friction. Eventually, when the applied force increases even further, the ball will eventually overcome static friction, and there will be a net force pointing out in the positive right direction. At the force of friction, it will become kinetic, and the ball will be launched out of the ruler with certain ejection velocity. This ejection velocity will be investigated further in my quantitative models. So first, let's have a simple rigid body model for this phenomenon. The assumptions of the rigid body model is 1, of course, rulers behave as rigid bodies. Secondly, we have the applied force load the beam quasi-statically. Thirdly, the rotational kinetic energy of the ball is negligible. First, let's go through the geometry of our system. L is the length of the ruler, and big M is the mass of the ruler. Small m is the mass of the ball, and r is the radius of the ball. The applied force, Fa, is applied a distance a away from the clamped end. The ball is tangent to the ruler a distance b away from the clamped end. And theta is the angle between the ruler to the horizontal, equal to arctan r over b. An important thing to note is that the system is symmetrical across the horizontal axes. now let's do rigid body analysis. We see that the torque of the applied force and the torque of the normal force from the ruler and ball are equal. It's giving us a torque balance equation here, Fa times A equals Fn times B. And overall, we have the net force profile equals the 2 times the horizontal projection of the normal force minus 2 times the horizontal projection of the friction force. Using these 3 equations, we derive the equation of motion as shown, and we can integrate the acceleration to get the ejection velocity. Since we already defined our equation of motion, we can solve this ordinary differential equation using a numerical method in Python. Here we numerically integrate it using the 5th order Runde-Kudai-Feinberg method. Here we use 4th order RK4 by using a 5th order correction for step size, which dynamically adjusts for step size. Now let's explore an Euler-Bernoulli beam model. The assumptions for the Euler-Bernoulli beam model are such. First, the ruler behave as linear elastic beams. Secondly, the applied force load the beam quasi-statically. Thirdly, the rotational kinetic energy of the ball is negligible. Fourthly, the rulers have uniform material properties. And lastly, the ball does not lose contact with the ruler. We're able to justify this last assumption in our appendix. Feel free to discuss more about this assumption in our discussion if you wanted to. With the governing static Euler-Bernoulli beam theory as shown, we can see E is the elastic modulus, I is the second moment of area, Y is the deflection profile, and MS is the bending moment. The deflection profile is a superposition of the deflection from both Fn and Fa, and thus we can guess the equation shown. By solving the full Euler-Bernoulli equation for the full deflection profile, we get the following piecewise equation. Note that the local tangential angle is theta s equals arctan of the derivative of y, as demonstrated in this diagram. We can also demonstrate the correctness of our deflection profile by plotting this in Python. We can see that it sort of looks like a cantilever beam, aka a ruler, with these given parameters. Note that how n and yx are interdependent to each other. Therefore, we have to solve normal force iteratively within our code. First, we start with a rigid body estimate. Fn0 equals P stands for Fa applied force times A over B. Secondly, we insert the Fnk into the piecewise Euler-Bernoulli beam equation to calculate Ys and Y'S. Thirdly, we compute the tangential angle theta p and theta n. Fourthly, we calculate for torque p and torque n, the torque, and lastly, we enforce torque balance and update the new normal force until normal force converges. Now we can see the torque from our force analysis. We can still get the net force as the net force equals 2 of the normal force minus 2 times the friction force, all in the horizontal component, because the vertical component of the force cancels out. And finally, we can get this equation of motion and integrate for velocity. And note for here we have to analyze the edge conditions, because even as the ball center of mass exit the ruler, the ruler still is tangent to the ball. Therefore, compute the horizontal projection of the ruler by integrating its cosine term, and we're able to apply force balance in the edge to get these equations. Note that edge analysis only apply as the ball center mass exits the ruler, but the ball center mass is still within the length of the ruler plus the radius of the ball. Here we also use a numerical solution to integrate velocity, again using the 4/5th order Runde-Kudai-Feinberg method with a stop condition at of xcom equals L plus R. Lastly, let's move on to our experiments and experimental theoretical verification. First, we varied the applied force against the ejection velocity, and we're able to see a clear trend, a clear positive trend. Note that our Euler-Bernoulli beam model, the rigid body model, critically underpredict the ejection velocity. However, our Euler-Bernoulli beam model predict the velocity decently well. However, note that it overpredict the velocity at high ranges, and we believe this is a source of error because Euler-Bernoulli beam model assumes small angle approximations, and therefore it breaks down at larger angles. The second parameter we varied is the applied force location. And here we can also see a clear positive trend in which the rigid body model underpredicts the force, but the Euler-Bernoulli model predicts decently well. However, still sort of overpredict the velocity even if it's within the error bar ranges due to the same reason of small angle approximation. Thirdly, we vary the disk contact point, aka B in our the variable B in our equations. We also see a clear negative trend as the disk is placed further and further away from the applied force. The ejection velocity will be less and less. Again, our rigid body model underpredicts the velocity, and our Euler-Bernoulli beam overpredicts. Note that we can only go from 16 centimeters to 30 centimeters due to geometric constraints. Our piston is placed around 15 centimeters, so obviously your disc cannot be placed before the piston, and our ruler is only 30 centimeters long, so your disc cannot be outside of the ruler. Here we can see the Euler-Bernoulli beam model overpredicts velocity due to the same reason of small angle approximation. We're also able to vary the radius of the ball, the radius of the ball versus velocity, and here we get a positive trend as well. We then vary the mass of the ball. We would then vary the mass of the ball by putting clay into our 3D printed discs, and we're able to see that has a clear downward trend. The more mass you have, the slower the ejection velocity. Lastly, we're able to measure the difference between the metal ruler and the plastic ruler. We can see that the plastic ruler generally have higher ejection velocities than the metal ruler because of a higher Young's modulus. Note that for our metal ruler, we aren't able to test the disc contact point between 15 centimeters and 20 centimeters because of a very high Young's modulus. We're not able to push the disc into the ruler that far and the static friction would not hold, and therefore it would just slip out. So therefore, we need to have a condition in which static friction holds, and that's we found to be around 20 centimeters. We also notice that at the lower, a higher disc contact point, the rigid body model and the Euler-Bernoulli beam model agrees more than a lower compared to a lower disc contact point because the fact you have larger deflection angles. Lastly, we found that there's more agreement for the metal ruler between these two models due to the fact that the metal ruler has a higher Young's modulus. Overall, here's my conclusion. I've thoroughly explored theoretical models, my experimental setup, and lastly, here are my references. Thank you so much for listening.
So my first question would be if you have actually proved that your experimental setup applies symmetrically on the both rulers, and that the rulers are actually symmetrically, because in some of the videos it seemed to not be the case. Do you have any type of further verification that the rulers are actually symmetrically?
It is symmetrical.
Okay, we're going to discuss on that later on. Thank you so much. Can your theory account for the fact that your force is applied time dependent, so that it's not one only force struck, but actually over a certain time rate?
Because the pressure is constant, we can assume the force to be generally constant. And because the time frames that this small of the ejection, we can say that it's pretty constant.
Okay, thank you so much. Do you consider air drag in your theoretical model for your, do you consider air drag for the ball after leaving the rulers?
Air drag?
Yes.
No, but I do have an appendix on air drag.
Okay, we can discuss on this later. In your rigid model, am I understand correctly that you assume that the rulers are not able to deform?
Yes, that's definition of rigid body.
Okay, thank you so much. Your theory has a contact point between ruler and the ball. Do you theoretically are able to predict it, or do you just assume it's the radius of the ball, so the highest point?
You mean we predicted that it's always in contact with the ruler? What exactly?
No, if you exactly know where the ruler touches the ball?
Okay. No, but I don't think that's a very significant issue.
Okay, thank you so much. Do I understand correctly that you apply sliding friction into your theoretical model?
Yes.
Okay. Where does the main acceleration happen during the acceleration? So on which part of the ruler is the ball the most accelerated on?
At the edge.
Okay, thank you so much. Okay, I think I'm finished. Thank you so much.
Thank you. Hello.
Ich brauche einen Block.
Can I turn off the mic? Or how do you mute the mic?
Okay, I'm going to start. So, hello and welcome to Team Germany's opposition speech on problem number 7, reported by Canada, the ruler cannon. So, for our task-specific expectations, we believe that it is important to explain the basic principle of transforming elastic energy into rotational and kinetic energy. As well, rather hard on the experimental side is a symmetrically application of the force and the actual methods of tracking the motion. We have some relevant parameters which are listed here, and for the theoretical modeling, the ruler deflection is neat because under the force impact, the ruler will deflect, and therefore the force in tangential direction increasing, shooting out the ball. So, on the experimental side, we generally believe that Daniel made a rather good job on this side, with variation of the most relevant parameters, for example, the radius of projectile, as well as the disk contact point. We additionally saw on video checking using some OpenCV tracking techniques, and the independent variation between the mass and radius, which is rather complicated, but he solved it through inserting different materials, which we like. Unfortunately, we missed the variation of the friction parameters, increasing the resisting force, so the ball gets ejected with a higher force you need to apply on, and connecting to that, also a missing investigation on an actual critical force may be needed to release the ball. Unfortunately, also, the investigation of the rotational movement was there, but only proven for one individual case, where we would have liked to seen for more different cases, for example, with higher forces, and therefore also possible higher rotational effects. And of course, that in this experimental setup, the rulers are not actually symmetrically bent, but rather asymmetrically, due to the fact that he's not applying from both sides the same force, and that his whole setup is blocking in one direction. And we're going to discuss on that later deeply in our discussion. On the theoretical side, we believe that Daniel made a good job with its good qualitative explanation using a free body diagram and explaining why the external force on the sides of the ruler needs at some point overcome friction to get the ball ejected, and he modeled the deflection of the beam using Euler-Bernoulli beam theory. Unfortunately, we believe his theory does not account for the exact contact point between ruler and ball, which is neat for this phenomenon, because if you assume that the ball would touch the ruler on the top of his radius, there would be actually no tangential component of the force. And the theory as well as not account for the time-dependent force. So of course, the force does not only act for one time step, but actually is loading up onto several more. Most importantly, actually, is a theory assumption which is not justified on slide 25, where he believes that all the rulers are symmetrically bent. We also don't believe that the quasi-static assumption he's using in a theory is applied, because modeling a dynamic Euler-Bernoulli beam is actually more tricky than one might think, and you could not just simply iterate through every single step, but actually need to account for the time-dependent boundary conditions, as well as the loading from the time force, as well as the time-dependent loading from both sides. Most importantly, but he was able to predict the velocity with a rigid body model, which we are not fully ensured by if that is actually possible, because you need a deformation of the rulers in order to actually increase the tangential force which is acting up onto the ball surface. So whether it is even possible to predict the velocity with a rigid body model will be discussed later on. In general, we believe that Daniel made a good job on the qualitative side. Unfortunately, only on the experimental side, only for the symmetry of the setup, as the TAL states, and on the rest side, he did rather good, with most of the relevant parameters varied, although there are still possible points for improvement there, such as the friction, as well as proper investigation onto rotational effects. However, in general, we believe that Daniel partially to mostly fulfilled this task. With that, I would like to then invite a reporter onto the stage. Okay. 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 Okay, so Daniel, during your connecting, I think we can already start to take a look at your experimental setup, where you showed us how you apply the force on the both sides of the ruler. And please, if you could show out that photo and video again. Yes, very shortly, yes. Okay, thank you so much. We're anyway going to come on to later that, so you're definitely able to make your point even more. Now I would like to start with the experimental setup and your symmetry of the actual rulers. So, because if you show it to us, if we take a small sketch, you have your, do we have another pen? Thank you so much. If we look at the both, could you please go to the experimental setup? Thank you. So you have the two rulers and you're blocking from one side, and with the other side you're having your actuator, right? So then I am not completely sure if this system is actually symmetrically, because of course that side will actually not get deformed, right? But you're fixing the clamped end, right? Yes. Yeah. So therefore, I wouldn't say, we can clearly see that the upper side of the ruler is way more deflected in the beginning than the downside of the ruler. So this side is way more deflected. We don't have a symmetry in the system which you're applying for your theoretical, investigations. Okay. In general, I agree with you, but I would hardly disagree with you on that, because on the one hand, you're of course taking the assumption that your theory is symmetrically. Therefore, on the one hand, the actual energy stored in the both rulers is not just 2 times of one ruler, but actually the sum of both differently deflected. And more importantly, if we have an asymmetric deflection here, the torques acting on the ball will not cancel out, and therefore it will definitely rotate and as well have a rolling friction inside onto the surface. That's at least what I would imagine. Okay, Daniel, it's okay. But but on the one hand, we saw it would be rotating. But my suggestion would be what I could imagine possibly doing, not fixing the clamped end actually, but actually make it movable. So in that way, when the force gets applied, also the whole system changes. And in the moment, directly before the ball gets ejected, I believe the whole system should be completely symmetric, because based on Newton's third law, there would be no other way for the whole thing to go. And therefore, we are able to eliminate the asymmetric effects. And nevertheless, I still believe that you could get your theoretical model even better working if you had the symmetry, because then you have no rotation applied onto there. Yes, I would believe that you leave it movable in the vertical direction. Yeah. Okay, but nevertheless, let's maybe go on to further talk. You presented to us a rigid body model, which you were explaining to me how does the ball get ejected when we have a rigid body model for the both rulers. Mm-hmm.
Between, I let the wooden board fall. Do you think that this will be ejected?
If you just let it fall onto the ball.
Like if I clamp it on one end and let it fall, like let it do this.
No, I wouldn't think that the ball gets ejected, but
I would think that the rigid body, this free body diagram will still apply, and therefore under certain conditions such as very low friction constants, the ball will still be ejected.
Okay, that is very interesting. Maybe let's talk about that a bit more, because let's say we have no force applied and the rulers are completely rigid, okay? And now the ball is in here and it doesn't get ejected. That means that the tangential, so we have these two forces here, and the tangential directions are in general smaller than the friction we have compensating the friction which holds the ball in the shape, okay? So what would now happen if we put on force onto the sides in a rigid body model?
In the rigid body model, because
if the rulers are not able to deform, how would anything change in that position?
If you apply force here by torque balance, this you can able to calculate. If you apply force Fa here by torque balance, you're able to calculate Fn in this case, and by Newton's third law, you're able to have Fn onto the ruler. You have Fn. This is theta, Fn sine theta.
Okay, so
2 Fn sine theta. This is net force. F equals 2 Fn sine theta minus 2 mu Fn cos theta.
Okay, so but would that mean that the actual deformation of the ruler is not so important as you stated? Because assumingly this rigid body model works also sufficiently okay with the experimental work, how important is then actually the deformation of the
It's quite important, as you can see sorry guys, I'm trying hard as I can to click my arrows. As you can see in my almost all my graphs, the rigid body model always underpredicts the velocity because the body doesn't account for the local deflection.
Okay, now therefore I would agree with you definitely. That is importantly, we can then of course if we apply force, the whole angles change in this proposition. This is what I was looking for. Thank you so much. Maybe we'll move on to 1 or 2 slides where you showed us the velocity independency of the position of the ball. Yes. To this contact point, that's what I meant. Okay, you said to us, why is this experimental theoretical comparison under-predicting? Now why is the Euler-Bernoulli beam theory over-predicting your experimental values, especially for lower this contact point?
Imagine these are elastic beams and a force is applied here. If your disk is very close to the force, that means that your local deflection will be very, very great. And therefore, we know that Euler-Bernoulli in the derivation of the Euler-Bernoulli beam model, it assumes small angle approximation. And therefore, small angle approximation, you approximate a sine curve as an x equals y curve. Okay. And therefore, here it deviates
therefore, I would agree with you. But what I was looking for, how do you we were on that in the beginning of the discussion? How do you actually determine the contact point between the ruler and the ball? What is the mathematical definition which to be given? Do you assume the ball to touch at the top of the ball, just at the highest radius?
I'm not exactly. I assume it touches here.
But how do you calculate the point where it touches?
Well, from the integration, you're able to integrate x. So
yeah, but they need to be a geometric constraint or not, because all that you stated were all time-dependent force investigations, but we know the geometric constraint.
To calculate x in every time step, but this will be the point in which it's contacting. Okay. And then you're able to use.
I think we're not quite getting there. I asked several times, so how do we actually determine what I could imagine? If this contact point is not rightly determined, then of course the whole theory would shift upwards, and therefore maybe the deviation between experimental and theoretical work could be explained.
Here, given you know this angle, and you know this,
Yes, yeah, I agree with you on that. But what I miss in your report is that you explain how you actually done it, because your theory only worked the force dependency. But nevertheless, thank you so much. I would like to move on. Your theory, velocity theory, often over-predicts, and we already came to the point. If you actually including air drag, and if so, or if so not, do you believe it is? Do you believe the air drag could be possible that your exit velocity is over-predicting?
I don't think so. I think air drag, if you do a rough estimate, should be quite negligible on the order of rotational energy. However, I do sort of consider air drag.
Yeah, but you're measuring translational velocity and not rotational. And I would very shortly, unfortunately we have to end shortly, but I would disagree with you, because you have very high velocities and mostly not too negligible surface area, so therefore air drag could sufficiently play a role, and also would explain why you only over-predict for higher velocities.
Here and this have different air drag, and here we can see small deviations between these two data given the same mass and radius. It plays a role, but very small role. Thank you.
But okay. Thank you so much. concluding remarks, for our conclusion of the discussion. We started by discussing the asymmetric bending profile. On the one hand, the theory assumption he is applying, and on the other hand, if these assumptions and justifications are actually given in his experimental setup. Also, whether with an unsymmetrically bending of the rulers, also rotation comes important, which he mostly neglects in his theoretical investigations. I suggested that the possibility of a free clamp could possibly solve that problem. For the rigid body model, we had a short disagreement between the actual possibility of an ejection in a rigid body model, but fortunately Daniel cleared that one up, and we came to the agreement that the balance of torques is the most important here. For the contact point, we unfortunately didn't come to a complete end in the discussion. Unfortunately, the experimental and theoretical overview was not shown. If he is able to determine the contact point, which is rather important for the theoretical experimental comparison and for the air jack, I still believe that this is important. However, we're disagreeing here on that fact. Thank you so much.
When you look at the video, the ball has a vertical component of velocity downwards. So which velocity do you take? Which velocity do you track for? Yes. Yes, which velocity you track? Only the one in the horizontal axis or... Okay, thank you. Could you play the video of your ejection? Any one video? Yes. Okay, do you observe that the ball always stays in contact with the ruler? Yes. Opponent, do you agree with their evaluation?
Of the contact point, if the ball,
the ball always stays in contact with the ruler.
Based on his report, we're not able to make that sure decision. Possibly stick-slip effect could occur.
But do you believe it's possible for the ball to leave the ruler's contact before it reaches the end of the ruler?
Yes, I believe that is possible.
And you agree that in that case his assumption would be incorrect, right?
Yes.
Yes. Okay. So, wait. Opponent, reporter, you say you can theoretically prove the ball does not leave contact with the ruler? Yes. Could you elaborate on this? Okay. I see. Thank you. So to both of you, just now you agreed that the angle was not important for the ejection condition. Like when you discussed and drew this on the board. Sorry, to the reporter first. Yeah. That you said that was the angle of the ruler makes to the ball, is that critical for the ejection? The local angle? Yes. So, opponent, you agree, right?
Yes.
You agree? Okay. Yes. To the reporter again, so you think that a rigid body can still cause the ball to eject? Yes. Opponent, you agree?
I'm not fully convinced. I still believe the deformation needs to be happened, so the force increases.
In tracking video, we take the magnitude of velocity.
Oh, okay. Magnitude of velocity, thank you. Do you have an equation for your ejection condition?
No.
As in, no.
But you can see that our numerical simulation can tell you when it's 0.
So like when it ejects?
You can see.
So, but you don't have an equation for this.
It just it's written within the code. It's just when it doesn't overcome static friction.
Okay. To clarify, did you account for the frictional force between the ball and the plane?
Yes.
No. Okay. Thank you. Should I just use the mic?
You have to handle mic, yes. All right, can I ask you to go to
Good afternoon, everyone. I'm Austin from Singapore, reviewing problem 7 Real Canon. So onto the strengths and areas of improvement for the report. I believe the report had a very good experimental scope, very many parameters that were important to the experiment. I believe that the report also had a very good experimental range with the parameters such as the radius of the disk and the many points of force application. I think it was also good that it was also very commendable that the reporter characterized the Young's modulus of his ruler as well as the kinetic and static friction coefficients, as this is very important to whether the ball in affecting the velocity of the ball and whether the ball will eject. However, I believe the report still had a few areas for improvement. Firstly, I believe that his qualitative explanation of the ejection was incorrect, as the deformation of the rulers are very important in allowing the ball to eject. And I believe that there's also some oversimplifying assumptions in his quantitative theory. And he also had a very asymmetrical experimental setup. Onto the opponent, he points out that the rigid body model cannot allow the ball to eject, and the deformation was crucial for a horizontal component of the force to go. Please ignore that point, sorry, that's a mistake. Onto some areas for improvement too, he incorrectly agreed with the qualitative assumption the reporter provided, and he did not explain why the quasi-static assumption is inapplicable because the kinetic energy of the rulers may be significant. He also provided some very limited suggestions, especially in determining whether the launching of the ball in a rigid body case is possible. So on to what happened in the discussion. They first started by talking about the asymmetry of the setup. And I do agree with the opponent here that that the asymmetry in the system is very significant, as the linear actuator is only placed on one side of the ball. And I also believe that this may cause the actual acceleration of the ball to be under the predictor. And the normal force and friction here will also cause some rotation of the ball. Next, they discussed about the condition of the ejection of the ball. And the opponent raised the point that the force balance due to friction causes the ball to eject. The reporter raised this point. So the reporter defended this point by saying this, but I disagree with both the reporter and opponent said, as I believe that the deformation of the rulers causing a changing contact angle is what is really necessary for a horizontal component causing this ejection. So I believe that the local angle the ruler makes to the ball is very important for this. Next, they discussed about the reporter's method of obtaining the contact point between the ball and the ruler. And the opponent raised the point that this contact point cannot be calculated. But I do agree with the reporter's explanation that this can be calculated geometrically, as they do so for the full profile of the ruler, and this contact point should be a purely geometrical, could be obtained purely geometrically. Next, they moved on to the point of air drag. And the opponent made the point that air drag in his system is significant and could account for some over predictions in the reporter's report. But I do agree with the reporter that air drag might be is likely negligible in his system, as it is a small force compared to the other forces in the system, such as the restoring forces of rulers and the friction between the ruler and the ball. Now on to some final verdicts for this problem. I believe the reporter gave a incorrect qualitative discussion on this phenomenon, and he did use a quasi-static Euler-Bernoulli beam model to model this. And the opponent did rightly point out some asymmetries in the opponent's setup and some oversimplifying assumption in his quantitative theory. But unfortunately, I don't believe the reporter has fully answered the problem statement due to the incorrect explanation of why the ejection of the ball occurs. Thank you.
And questioning. So this opponent raised a few concerns. First, regarding the asymmetric ruler profile, which unfortunately we're not able to solve due to our experimental limitations. However, we believe this small asymmetry of the system is not a very large issue. Secondly, they recommended fixing the clamp by having a degree of freedom in the vertical direction. However, I believe that will introduce a very large degree of freedom to the system, which are not necessarily controllable. The best solution would be to use two symmetric pistons. Thirdly, did not believe in the rigid model that results in velocity rejection of the ball. However, we clarified the ball can be ejected given a frictional constant constraint. Fourthly, it talked about how the rotational movement caused by the asymmetric of ruler profile. However, we're able to confirm that the amount of energy lost due to rotational motion was minimal. Fifthly, they raised concerns about the exact contact point. Unfortunately, we didn't understand that at first, but afterward we clarified it can be solved using trigonometry and just geometry overall by the position tangent to the circular projectile. Sixthly, they discussed the role of air drag and we determined it as it plays a small role. And we also observed between the spherical and the cylindrical ejection that it will be interesting to explore further the role of air drag. The reviewer raised some concerns about, one, what dimension of velocity we use, and we'd like to clarify we use the magnitude of the vector. Secondly, they have concerns about the continuous contact of the ruler, and clarified in our appendix slide, both theoretically and experimentally camera tracked to confirm to not lose contact throughout all of our experiments. Lastly, I feel like the reviewer was a little bit confused about our rigid body model and was down for just intuitive understanding only. Our actual model with predictive power was the Euler-Bernoulli beam model. Overall, I'd like to thank the opponent and the reviewer for, again, another fruitful discussion, and thank you so much for this amazing physics fight.
Thank you very much. Could I ask the reporter to connect his presentation again, and then we will have 5 minutes for jury questions. Could I ask also all the other two attendees to go on stage? Questions from the jury? Then let's start over here.
Reporter, can you just show me slide number 9? Basically, I want to understand the graph. You have drawn a graph over there. There was a graph along with this presentation. Yeah. Can you just explain those ups and down between after 4.3? If you look at the upper graph. Yeah, that one. Yeah. Why it goes down after that point? Yeah, that particular position.
Yeah.
Okay.
When you were solving the dynamic model, what did you take as an initial condition for the shape of the ruler? And I want the top one and also the bottom one. How did you get the initial shape of the ruler?
Assume to be straight.
Initial. Yes.
Okay, thank you.
Question for the reporter. In your experiment, how do you end your additional force? Yes, in your experiment setup, how do you add additional force? Okay, thank you.
I have a quick question for the reviewer. You mentioned that he should consider the local angle, but at the same time you said that he modeled the shape. So what do you mean? What is then, is that the same thing, or what are you referring to? Just very quickly, is there any difference, or between the shape? If you have the shape, don't you also have the local contact angle?
To the opponent, you mentioned that the theory did not consider time-dependent force. What do you mean by time-dependent force?
Okay.
Which force are you saying?
What I mean is the force is like it's pushing down onto the ruler. That means that the ball is also starting to accelerate during the deflection profile is changing in this quasi-static simulation, which he did not account for because he just said, okay, we have one force and then it starts to accelerate, but it actually the force builds up at some point, and during the time it also starts to accelerate. This is what he thought.
Will it give bigger velocity or smaller velocity if you consider that?
I believe there would be so the exit velocity could be the same, but in general I believe the velocity would be slightly smaller. Yeah.
Thank you.
Any of the first-time jurors, does anybody have a question they wish to ask? Yep.
This is a question to the to the reporter, in your experimental setup, you mentioned something about a glass plate. I didn't. Could you clarify a bit more?
To the wooden board, which acts on the ground, so it just basically reduces the friction between the disc and the ground.
Any further question? Lan, do you have a question? Oh, then we can go here.
Can you go to slide 40, please? 40, 40.
So here it is visible that for big contact points, so like the 24, 26, 28, 30 maybe, the theory agrees better with the rigid body model than for like 16, 18 and so on. Can you explain the reason why it is like rigid body model is good till maybe approximately 22?
So rigid body model is have best predictive power when the ruler is similar to a rigid body, aka doesn't have very large deflection angles. And therefore, when your ball is really, when your disc is really far away from the applied force, the deflection isn't very large compared to if it's very near the piston. And therefore, it will be more similar to a rigid body and therefore has a larger predicting power.
Okay, I think we're out of time. Thank you very much.
We will proceed to grading. out the grade? Starting from my side, okay. All right, then can I ask you to show me the grade for the report, please? 7, 6, 7, 8, and 5. All right, then next for the opponent, please. 7, 6, 6, 8, and 6. And finally, the grade for the review, please. 6, 8, 8, 9, and 8. Can I ask you for this sheet, please? I'll give it back to you. I just need it for the question. All right. Thank you very much. For the report, we have a single 8. Mladen, could I ask you to?
Overall 7.7 rounded up. I think that it was a pretty decent report. No remarks, although there was a pretty good discussion about the asymmetricity and its significance. I think that it was a pretty decent, and congratulations on the good work.
Yeah, my partial grades were 2.5 for presentation and 1.6 for discussion with the opponent. And so overall it is coming around 5.1, and I've rounded up to 5. For me, I was expecting to have a more discussion where there was a lot of confusion about different forces, as the opponent has pointed out initially. But later on, I think the discussion was not done properly on those topics.
Thank you very much. Then for the opponent, we are between 6 and 8. Mladen?
Well, I suppose I'm calibrated a little higher. Partial scores 1.7, 2.9, plus 3, minus 0.2, overall 8.6 rounded down.
Okay. Becca, can I ask you for a comment?
Yes. So I gave the opponent 1 for questions asked because I don't think that the time was used sufficiently. Then 3 points and 2 points for 3 points and 2 points for the discussion. Discussion was like the beginning of discussion was very good. But then there were, the thing that I didn't like most was that you didn't talk too much about experiments. And the reporter, when he reported, he spent like too few time on the experiments, and I wanted it to be discussed more. And then like minus 0.5 for the question that I asked you about the time-dependent force, because your answer was it wouldn't change the velocity. Then like, why do you point it out in the presentation? Okay.
All right. If there are no questions to the opponent, then let's move on to the review. We again have Mladen here.
9, yes. It's partial scores 1.8, 2.6, 1.6, 1.6, plus 0.4, and then overall 8.8.
Yeah. For the review, I was on the lower side. What I did not really like that much was in the questions I gave you 1 point because I thought some of the questions were already discussed in quite some detail during the discussion. So it was a bit of repetition in that sense. So the partial grades was 1 for the question, 125 for the report, 125 for the opposition, and 1 for the discussion analysis. So also the thing with this local angle versus you have the whole profile. This was one of the main points you were criticizing him for. But for me, it was not clear what you're actually referring to. And then there were quite some similarities already with the opposition. So if you have criticisms on his theory, then you need to also convey why it's relevant, like in very concise terms, and not just say we think it's important, but also try to say why it is important and like what I don't know, effect would I see if I would include that in the model. Any questions from any of the students? You will get a break, yes. Most important question. All right, then thank you all for this first stage. You will have a 10 minutes break, and then the doors I think are locked, right? So you have to knock if you want to re-enter. But yeah, there are enough people in here. You will. Question to the teams. Do you want to switch spots? If one of you wants to switch, we can switch. I don't really care, up to you. Everybody fine? I'll leave it up to you. It's either way. The place is almost equivalent. Yes, thank you.